Hey everybody, wanted to spend a little time going over question 14.22 out of Brown-LeMay-Burston. And this one is good because it kind of highlights the difference between average rate of change and instantaneous rate of change. Okay, so this one may be a little longer because it's asking us to graph down here. So I may actually, this may be a little longer than what we want, but let's start here at the A. Okay, it says calculate the average rate of the reaction in molarity per second for the time interval between each measurement. Okay, and so for A, it's between each measurement. So average rate is equal to the change in concentration over the change in time. That's going to give us the rate. Okay, but we want it in seconds. So this interval is, this is where I need my calculator. Well, I don't really need it, but I'm going to show you how to do this. So it's 54 minutes times 60 seconds in a minute. And so this is going to be 3,240 seconds. And what's the change in concentration? Well, 1.85 minus 1.58. Okay, and that's 0.27. So now we just plug it in and we get change in concentration, 0.27 over 3240, and let's do the math. So 0.27 divided by 3240, and that gives us a rate of 8.3 repeating times 10 to the negative fifth. Okay, now we repeat that process, okay, for here. So that is 53 minutes times 60 seconds. Okay, and this change in so that's 3180, and that change in concentration is 0.22. So for this next one, it's 0.22 over 3180. Okay, 0.22 divided by 3180. And that answer is equal to 6.9 times 10 to the minus 5. Okay, and these are all in molar per second. And now the third one, okay, that change in time is 108 seconds, or 108 minutes. So 108 times 60, okay, is now 6,480 seconds. And the change in concentration here is 0.34. So 0.34 over 6480. Okay, so 0.34 divided by 6480 is equal to 5.2 times 10 to the minus 5. Again, molar, capital M molar per second. And this pattern stands to reason because as the reactants are used up, the rate in which they're used up will change over time. Okay. Now, let's see. The last one here is 215 minutes times 60. Okay. And so that gives us 1290, and the change there is 0.46. Yeah. So 0.46. So it's changed more, the concentration has changed more, but it's done so over a longer time, so 12,900. So 0.46 divided by 12,900, and that equals 3.5 times 10 to the minus 5 molar per second. And so that stands to reason there that that change is decreasing through the whole thing. And then it says, calculate the average rate of reaction for the entire time of the data. Okay, so the average rate of change is the change in concentration over the change in time. So for part B, and I'll do that here, okay, so the average rate is, let's see, so we do 1.85 minus 0.58. And that's, so the So the change in concentration is 1.27 over the time is 430 minutes, but we want it in seconds because I'm sure we're going to be asked to compare. And so that's 2 over 25,800 seconds. It sounds like a song. Okay. 25,800 seconds. Okay, anyways, if you get the reference, good for you. Okay, so 1.27 divided by that number, okay, gives us 4.92 times 10 to the minus 5, okay? And so that's the average over that whole time. It says, which is greater, the average rate here, so the third one that we did, this one, or this one? Oh, wait, I'm sorry. Or 107 to 1, okay. And this we actually don't have to, we do because we're going to skip 2. Okay, so for C now, okay, I'm going to erase this because I'm running out of space here. So for part C of this question, now we're comparing this one to this one, okay? And so here, we should already know that the average rate for the one that is happening earlier is going to be greater. But let's show that, okay? So 54, 215, so we'll find the difference between that. 215 minus 54, that gives us 161, okay, times 60, because we want a time, so that's 9,660, and the change in concentration is 0.56. So 0.56 divided by that answer gives us 5.7, 5.8, right? Yeah, 5.80 times 10 to the negative 5. And again, that's in molar per second. Okay, and now we're going to do the same thing for 107 to 430. So let's see, 430 minus 107 gives you the change in time. But then we have to multiply by 60 because we want it in seconds. So it's, let me extend this down a little bit. So this is going to be over 19,380 seconds. Okay, and the change in concentration here, okay, 1.36 minus 0.58. Okay, and so we get that over 0.78. We do the division, so that divided by 19,380 seconds, and we get 4.02 times 10 to the minus 5. So that shows us what we already knew. This rate is slightly greater than this rate because this happens while there's more concentration, and so this rate is greater. Okay. Now, it didn't ask us to calculate it. I showed you how to calculate it as supporting evidence. Okay. So now, here it is. Now we want instantaneous rates. Okay. It says graph this versus time and determine the instantaneous rates in molarity per minute and molarity per second at 75 seconds and at 75 minutes and 250 minutes. So to answer this question, what I've done is I've set up a graph. I've actually graphed the data in the problem, and I think that just so you can see, it's easier for me to show you that I do this by hand. Okay, and if I could write rate of reaction here. Okay, and so I made a mistake here, so that should be a thing. But notice that this is some sort of curve, okay, where the rate here, this kind of supports the answers to A, B, and C. The rate here, the slope at this point, is steeper than the slope here, okay? Now, the question asks about 75 minutes and 250 minutes. So 250 minutes, if I can write this correctly, goes here. So that's this line. And then 75, oh, I'm going to do this in pencil. So 50 is between two 50s here. Okay. And now 75, that's 50. And here's 75. So we're going to go up here. We're going to do this. Okay. And so the way to find the rate at this point, the instantaneous rate, is to take this and then draw a tangent line at this point. Okay, and I know this is kind of a big pain in the neck, but that's what you do. Okay, and then you draw a tangent line. Then you go back again to algebra here. Okay, maybe geometry. And then when you do that, you now have that. And so that rise over run here. And then this one, let's see, we got this. Goes to there, it looks like. Okay, so rise over run. And so now we do some math here. So this is 1, 2, 3, 4, 5, 6, 7. So that's 7. So my scale, that would be 100 minutes. And then changing concentration, this is 1, 2, 3, 4, 5, 6. So 6, I think my scale, 1, 2, 3, 4, 5, 6, 7 is still 7. So 6/7 of the way to 1.5. So 0.5 times 6 divided by 7. Okay, so 0.42. So this is, the change is 0.43. Okay, because if we look, you can see, okay, 0.43. Cool. Okay. And so that is the change in concentration. So now let's do that. We don't need a calculator to do that. 0.43 divided by 100 is 0.0043 molar per minute. Okay, and that's the instantaneous rate of change there. And then now for this one, let's see, so 1, 2, 3, 4, 5, 6. So that's going to be 6/7 of 100, right? Because it's 6/7 of the way here. So 100 times 6 divided by 7. So that's 85 is the change there. Okay, so that's the change in time is 85 minutes. And now we go, the rise is 3, okay, but it's not 3, it's 3/7. Okay, so it's 0.5 times 3 divided by 7, and so it's 0.21. Okay, concentrate molar. Okay, so 0.21 divided by 85 equals 0.00225 molar per minute. And that stands to reason. The slope of this line is steeper than the slope of this line. And what we have found in this whole question is that as the reaction progresses, the rate of the reaction slows down. Okay? And so that's what's happening here. Okay? And so I guess the last thing it asked us to do is to convert this into molarity per second. So now we're going to take that and we're going to multiply every 1 minute 60 seconds. Okay. So we're going to take 0.0043 molar per minute, and for every 1 minute we get 60 seconds. So then we divide by another 60, and so now we get 7.17 times 10 to the minus 5 molar per second. We do the same thing here, 0.0025 divided by 60, and we get 4.17 times 10 to the minus 5 molar per second. So in this case, I think it's really good to just use paper and pen and get paper dirty, and there it is. And so have a great day, everybody.